Lab-on-a-Chip devices integrate multiple laboratory functions onto a single microchip by combining microfluidics, microelectronics, and micro-optics. For example, a chip in a pharmaceutical lab can synthesize, separate, and analyze chemical compounds in one compact platform, much like a Swiss Army knife that houses many tools in one convenient multifunctional unit. At the microscale, fluids behave according to laminar flow dynamics because viscous forces dominate over inertial forces. For instance, two colored liquids injected into adjacent microchannels flow in smooth parallel layers without turbulence, much like cars moving in well-defined lanes on a quiet one-lane road. Diffusion is the primary mixing mechanism in lab-on-a-chip systems due to the absence of turbulence. For example, a drop of dye slowly disperses into a clear solution in a microchannel, similar to how a drop of ink gradually fades into water, ensuring gentle and uniform mixing over time. Photolithography is crucial in fabricating microchannels by transferring detailed patterns onto substrates with micrometer precision. For instance, engineers etch intricate network designs onto a silicon wafer, much like using a finely cut stencil to spray paint a complex image on a surface. Soft lithography employs flexible materials like PDMS to mold microchannel patterns rapidly and cost-effectively. For example, researchers create disposable chips for biochemical assays by casting PDMS on a master mold, much like producing a rubber stamp that reliably reproduces a detailed design over and over. Material selection in lab-on-a-chip devices is key to performance, with choices like glass offering chemical resistance and PDMS providing ease of fabrication. For instance, a glass chip is used for high-temperature reactions, while PDMS is chosen for optical transparency in bioassays, much like selecting cast iron for searing versus nonstick pans for delicate cooking. Pressure-driven flow uses a controlled pressure gradient to move fluids through microchannels. For example, a syringe pump delivers precise nanoliter volumes of reagents to reaction sites on a chip, much like squeezing a tube of toothpaste produces a steady, predictable stream. Electrokinetic methods, such as electroosmosis, use electric fields to move fluids by interacting with the electrical double layer on channel walls. For instance, applying voltage can drive an electrolyte solution through a microchannel without mechanical parts, similar to an invisible force gently pushing water along a narrow stream. Acoustic actuation leverages high-frequency sound waves to create localized pressure variations that drive fluid movement. For example, surface acoustic wave SAW devices rapidly mix reactants in a microreactor, much like ripples from a pebble tossed into a pond, stir and blend the water. Thermal gradients in microchannels induce convection by creating temperature-dependent density differences. For example, localized heating on one side of a chip generates a gentle flow that enhances mixing, much like warm air rising in a room causes a natural circulation of air currents. Droplet microfluidics partitions fluids into discrete droplets that act as isolated reaction vessels. For instance, a TJ junction device generates uniform water droplets in oil, each serving as a tiny reactor, much like an array of mini test tubes performing parallel experiments. The formation of uniform droplets is governed by the balance between interfacial tension and shear forces. For example, a flow-focusing device creates droplets of precise size ideal for reactions, similar to how atmospheric conditions determine the uniform size of raindrops in a gentle shower. Sequential chemical reactions can be integrated on a single chip by arranging multiple reaction chambers in series. For example, a chip may first synthesize an intermediate and then mix it with another reagent downstream, much like an assembly line where each workstation adds a specific component to build a final product. Integrated sensors on lab-on-a-chip devices allow for real-time monitoring of parameters such as pH, temperature, and concentration. For instance, an optical sensor can detect color changes during a reaction, providing instant feedback, much like a car's dashboard displays real-time information to guide the driver. Miniaturization in lab-on-a-chip systems drastically reduces the volume of samples and reagents required. For example, reactions may occur in nanoliter volumes, minimizing waste and cost, much like gourmet cooking uses precise, minimal ingredients to create exquisite dishes without excess. High surface area to volume ratios in microchannels enhance reaction kinetics by promoting efficient heat and mass transfer. For example, microreactors can achieve faster synthesis than bulk reactors, much like a pressure cooker speeds up cooking by maximizing contact between food and heat. Lab-on-a-Chip devices are ideal for environmental monitoring because they can integrate sampling, pre-concentration, separation, and detection on a single platform. For example, a chip can analyze trace heavy metals in water with high sensitivity, much like a high-powered microscope reveals details invisible to the naked eye. Integrating chemical synthesis and analysis on one chip enables immediate feedback and iterative optimization. For instance, a chip that synthesizes a compound can instantly assess its purity through embedded detectors, similar to an assembly line that continuously checks product quality before packaging. Precise microchannel design ensures accurate fluid routing and mixing, as engineers tailor channel geometries to specific applications. For example, serpentine channels can enhance mixing by forcing fluids to repeatedly change direction, much like a winding road slows traffic and directs vehicles safely to their destination. Incorporating nanomaterials into Lab-on-a-Chip devices can enhance performance by catalyzing reactions and improving sensor responsiveness. For example, a graphene coating may increase detection sensitivity while reducing fouling, much like adding a catalyst speeds up a chemical reaction by providing an optimal reaction surface. Lab-on-a-Chip platforms facilitate combinatorial synthesis by enabling parallel testing of multiple reaction conditions. For example, an array of microreactors can screen various catalysts simultaneously, much like several mini-ovens testing different recipes to determine the best outcome. The energy efficiency of Lab-on-a-Chip devices is high because minimal volumes require less power for processes like heating and cooling. For instance, a microreactor consumes a fraction of the energy of a traditional reactor, much like LED lighting provides bright illumination while using far less electricity than incandescent bulbs. Rapid thermal cycling is possible in Lab-on-a-Chip devices due to their low thermal mass, which allows for swift temperature changes. For example, microheaters can quickly alternate between high and low temperatures during PCR. Much like a thin metal sheet heats and cools rapidly compared to a bulky object, high-throughput analysis is enabled by the parallel architecture of Lab-on-a-Chip systems where multiple microchannels operate simultaneously. For instance, a single chip may run dozens of assays at once, much like an assembly line produces multiple products concurrently to boost productivity. Customizable chip design allows Lab-on-a-Chip devices to be tailored for specific applications by integrating different functional modules. For example, a chip designed for catalytic reactions may include specialized zones for mixing, heating, and detection, similar to building a custom computer where each component is chosen for optimal performance. Integrated optical components such as waveguides and photodetectors enable sensitive spectroscopic analysis on chip, for instance. An optical sensor can monitor subtle changes in light absorption during a reaction, much like a digital camera captures high-resolution images by detecting minute variations in light. Electrochemical sensors embedded in Lab-on-a-Chip platforms provide precise analyte detection by measuring electrical signals from chemical reactions. For example, a chip can detect trace pollutants by recording current changes, similar to a sensitive smoke detector that alerts at the slightest hint of smoke. Microfluidic valves control fluid routing with high precision by opening and closing channels on demand. For instance, pneumatic valves can direct reagents to specific reaction chambers in a controlled sequence, much like traffic lights regulate vehicles at intersections to ensure smooth and orderly flow. Surface modifications such as silicization or polymer coatings adjust the wettability and chemical reactivity of microchannel walls. For example, treating a glass channel to become hydrophobic prevents unwanted adsorption of biomolecules, much like a non-stick coating on cookware prevents food from sticking and makes cleaning easier. Lab-on-a-Chip devices enable detailed kinetic studies by capturing transient intermediates in a controlled microenvironment. For instance, A chip can monitor a fast catalytic reaction in real time, much like a high-speed camera reveals the rapid motion of a hummingbird's wings, uncovering details normally too fast to observe. Magnetic manipulation within Lab-on-a-Chip systems allows for selective control of magnetically responsive particles. For example, magnetic beads coated with antibodies can be guided to capture specific proteins, much like using a magnet to pull metal filings from a mixture, enabling targeted separation and analysis. On-chip chromatographic techniques separate complex mixtures by exploiting differences in chemical affinities. For instance, a microfluidic chromatography module can isolate individual compounds from a sample, much like a sieve sorts particles by size to separate materials into distinct groups. High-dissolution computational fluid dynamics (CFD) simulations are used to optimize chip designs by predicting fluid behavior. For example, engineers simulate serpentine channel flow to maximize mixing efficiency before fabrication. Much like flight simulators help pilots perfect maneuvers prior to real-world flights, Lab-on-a-Chip platforms provide ideal conditions for studying non-Newtonian fluids whose viscosity changes with shear rate. For example, polymer solutions can be analyzed under varying flow conditions, similar to how ketchup flows more easily when a bottle is shaken, revealing its shear thinning behavior. Modular design in Lab-on-a-Chip devices allows for rapid prototyping and reconfiguration of functional units. For example, researchers can swap out a mixing module to test different geometries without redesigning the entire chip, much like building with Lego blocks where pieces can be rearranged to create new structures. Real-time data analytics integrated into Lab-on-a-Chip systems enable automated process control based on continuous sensor feedback. For instance, an AI-driven chip might adjust flow rates or temperatures in response to live pH measurements, similar to a smart thermostat that continuously fine-tunes home heating to maintain an optimal climate. The compact size of Lab-on-a-Chip devices results in significant energy savings, since minimal volumes require less power for thermal management and fluid movement. For example, a microreactor operates on a fraction of the energy of a conventional reactor. Much like modern energy-efficient appliances provide robust performance with much lower power consumption. Precision microfabrication techniques ensure high reproducibility across Lab-on-a-Chip devices by producing uniform channels and reaction chambers. For instance, mass-produced chips yield nearly identical experimental conditions, much like precision-engineered parts in a high-performance engine work in harmony for reliable operation. Integrating Lab-on-a-Chip devices with mass spectrometry enables direct high-sensitivity chemical identification by coupling on-chip sample preparation with mass analysis. For example, a chip can pre-concentrate and ionize analytes before transferring them to a mass spectrometer, much like an assembly line immediately inspects products for quality assurance. Lab-on-a-Chip devices can be engineered to operate under extreme conditions by using robust materials and innovative designs. For instance, a silicon-based chip may withstand high pressures and corrosive chemicals in industrial synthesis, similar to a deep-sea submarine built to endure the crushing pressures of the ocean depths. Detailed investigation of reaction mechanisms is facilitated by Lab-on-a-Chip devices that capture transient intermediates with high temporal resolution. For example, a chip may reveal a short-lived reactive species during a complex synthesis, much like a high-speed camera captures rapid movements to expose details invisible to the naked eye. High-throughput catalyst screening is revolutionized by Lab-on-a-Chip platforms that allow parallel testing of multiple catalyst formulations. For instance, an array of microreactors can evaluate various catalysts simultaneously under identical conditions, similar to a racetrack where several runners compete side by side to determine the fastest. Optimized microchannel geometries such as herringbone patterns significantly enhance mixing efficiency by inducing chaotic advection even in laminar flow. For example, a herringbone mixer increases the interfacial area between reactants, much like a mechanical blender rapidly homogenizes ingredients to produce a smooth mixture. Integration of separation and detection modules on a single chip stream lines analytical workflows by performing both functions in a continuous process. For instance, a lab-on-a-chip device might first separate analytes via electrophoresis and then detect them optically, much like a sorting machine that filters and inspects products in one seamless operation. The integration of lab-on-a-chip devices into automated systems facilitates continuous, real-time control of chemical processes across multiple chips. For example, a network of microreactors can be managed by centralized computer systems to optimize production, similar to a smart factory where interconnected devices work together for maximum efficiency. Surface interactions and wettability in lab-on-a-chip devices can be finely tuned through chemical modifications to optimize fluid flow and reaction efficiency. For example, modifying a channel surface to be hydrophilic or hydrophobic can control reagent distribution, much like treating fabric to repel water ensures that moisture does not saturate it. Integrated optical detection methods such as interferometry or surface plasma resonance enable label-free monitoring of molecular interactions on chip, for instance. An SPR sensor can detect the binding of biomolecules in real time without fluorescent tags, much like a mirror reflecting subtle changes in light reveals details without extra adornment. Combining multiple separation techniques on a single lab-on-a-chip platform enhances the resolution of complex mixtures. For example, a chip may sequentially employ electrophoresis and microfluidic chromatography to isolate compounds, much like using a series of increasingly fine sieves to progressively refine a raw material. Real-time monitoring and dynamic adjustment of reaction conditions are possible with continuous sensor feedback integrated into lab-on-a-chip devices. For instance, a chip can automatically modify reagent flow in response to live temperature and pH data, much like an autopilot system constantly recalibrates a plane's course based on changing atmospheric conditions. Future lab-on-a-chip devices will incorporate advanced nanomaterials, quantum sensors, and AI-driven analytics to enhance functionality and precision. For example, next-generation chips might integrate quantum dots for ultra-sensitive detection and machine learning algorithms for predictive control, much like modern smartphones combine diverse high-tech functions into one transformative compact device. Multiplexing capabilities in lab-on-a-chip systems allow simultaneous detection of multiple analytes in one assay. For instance, a chip can incorporate several sensor arrays that detect different biomarkers at once, similar to a multi-channel radio that receives various stations concurrently. Digital microfluidics manipulates droplets on an open surface using electrical forces rather than physical channels. For example, electrodes arranged in a grid can move, merge, or split droplets on a chip, much like a digital chessboard where each move is precisely controlled by electrical signals. Biosensor integration in lab-on-a-chip devices enables sensitive detection of biological molecules such as DNA, proteins, or pathogens. For instance, a chip can be functionalized with specific antibodies that bind to target molecules, much like a lock and key mechanism where only the correct key molecule can trigger a detectable response. Point-of-care diagnostics using lab-on-a-chip technology offer rapid on-site testing with minimal sample preparation. For example, a portable chip can analyze a drop of blood for glucose levels in minutes, similar to a home pregnancy test that delivers immediate results with high reliability. Lab-on-a-chip devices have transformative applications in healthcare by enabling personalized diagnostics and treatment monitoring. For instance, a chip can analyze patient-specific biomarkers to tailor drug therapies, much like a bespoke suit is custom-fitted to an individual's measurements for optimal performance. Rapid prototyping techniques in lab-on-a-chip fabrication allow researchers to iterate designs quickly and efficiently. For example, 3D printing can produce a new chip design within hours, much like a sketch artist can rapidly create multiple drafts of a portrait until the perfect likeness is achieved. Low-cost production of lab-on-a-chip devices is possible due to advances in microfabrication and scalable manufacturing methods. For instance, roll-to-roll processing can mass-produce disposable chips for diagnostics. similar to printing newspapers, where thousands of copies are produced quickly and economically. Portable diagnostic devices based on Lab-on-a-Chip technology enable field testing in remote or resource-limited settings. For example, a handheld chip can rapidly detect infectious diseases in rural clinics, much like a compact GPS unit guides travelers through uncharted terrain. Lab-on-a-Chip systems are advancing personalized medicine by providing real-time monitoring of patient biomarkers. For instance, a wearable chip can continuously measure blood analytes and transmit data to healthcare providers, much like a smartwatch tracks heart rate and activity levels to provide personalized fitness insights. Integration with smartphones allows Lab-on-a-Chip devices to leverage mobile computing power and connectivity for data analysis and remote diagnostics. For example, a chip can transmit test results via a smartphone app to a doctor, much like a smartphone camera captures and shares high-quality images instantly over social media. Micro-total analysis systems, MTAS, represent the convergence of all laboratory functions on a single chip, enabling complete chemical analysis from sample to result. For instance, a MTS device can extract, amplify, and detect genetic material from a sample, much like a miniaturized laboratory performing the entire workflow within a single integrated system. Droplet merging and splitting in Lab-on-a-Chip devices allow for controlled reagent addition and sample division. For example, two droplets can be precisely merged to initiate a reaction or split into smaller volumes for parallel testing, much like mixing ingredients in a recipe or dividing a large cake into equal slices for uniform servings. On-chip reagent storage provides a means to preload Lab-on-a-Chip devices with necessary chemicals, enabling fully automated assays. For instance, micro-reservoirs integrated into the chip can release precise volumes of reagents at predetermined times, much like a time-release capsule delivers medication gradually over time. Autonomous operation in Lab-on-a-Chip devices is achieved through integrated microprocessors and control systems that manage fluid flow and reactions without human intervention. For example, a fully automated diagnostic chip can process a sample from start to finish, much like a self-driving car navigates traffic without driver input. Multi-step synthesis on a Lab-on-a-Chip platform allows complex chemical reactions to be performed in sequence with high precision. For instance, a chip can sequentially add different reagents to build a complex molecule, much like a multi-stage rocket that performs separate maneuvers during its ascent to reach orbit. High-sensitivity detection is a hallmark of Lab-on-a-Chip devices, enabled by integrated sensors and miniaturized reaction volumes. For example, a chip may detect trace levels of toxins in a sample with remarkable accuracy, much like a finely tuned scale that can measure even the smallest weight differences. Chip-to-chip integration allows multiple Lab-on-a-Chip devices to be networked together for complex analyses and large-scale processing. For instance, several chips can work in tandem to screen thousands of samples simultaneously, similar to a distributed computing network that harnesses the power of many processors to solve complex problems. Microfluidic mixers within Lab-on-a-Chip devices are designed to enhance the contact between reagents, ensuring rapid and complete reactions. For example, a mixer with a zigzag channel forces fluids to repeatedly change direction, much like a chef vigorously stirring a sauce to achieve a uniform blend. Integrated heaters and coolers in Lab-on-a-Chip systems provide precise temperature control, which is critical for many chemical and biological reactions. For instance, microheaters can maintain a stable environment for enzymatic assays, much like a thermostat in an incubator ensures that newborn animals are kept at the perfect temperature. Thermal management strategies on Lab-on-a-Chip devices are essential to dissipate excess heat from exothermic reactions. For example, a chip may include microchannels specifically designed for coolant flow, similar to how a car's radiator disperses engine heat to prevent overheating. On-chip polymerase chain reaction, PCR, amplifies DNA rapidly and with high specificity using miniaturized thermal cycling. For instance, a Lab-on-a-Chip PCR device can generate millions of copies of a DNA segment in minutes, much like a high-speed photocopier reproduces documents quickly and accurately. Digital PCR on Lab-on-a-Chip platforms provides absolute quantification of nucleic acids by partitioning the sample into thousands of individual reaction chambers. For example, each chamber acts as a mini PCR, and the collective results yield precise quantification, similar to counting individual beads in a jar to determine their total number. Lab-on-a-Chip devices are transforming genomics by enabling rapid sequencing and analysis in a miniaturized format. For example, a chip can process and analyze genetic material from a single cell, much like a high-powered microscope reveals intricate details of cellular structures. In proteomics, Lab-on-a-Chip platforms allow for the detailed study of proteins through integrated separation and detection techniques. For instance, a chip can isolate specific proteins from a complex sample and analyze them in real time, similar to sorting and identifying individual instruments in an orchestra. Lab-on-a-Chip devices are pivotal in metabolomics by facilitating the rapid analysis of small molecule metabolites from biological samples. For example, a chip can detect subtle changes in metabolic profiles in response to drug treatment, much like a sensitive balance that detects minute differences in weight. Microfluidic cell culture on Lab-on-a-Chip platforms enables controlled growth and analysis of cells in a miniaturized environment. For instance, a chip can mimic tissue conditions to study cell behavior and drug responses, much like a miniature greenhouse simulates natural conditions to nurture plants. Organ-on-a-Chip devices extend Lab-on-a-Chip technology to mimic the functionality of human organs, providing realistic models for disease and drug testing. For example, a lung on a chip can replicate breathing motions and gas exchange, similar to a highly detailed model that simulates organ function for research. Lab-on-a-Chip platforms are revolutionizing drug screening by providing high-throughput, low-volume assays that mimic in vivo conditions. For instance, a chip can test multiple drug candidates on cultured cells simultaneously, much like a multi-well plate used in traditional assays, but with far greater precision and speed. Enzyme assays on Lab-on-a-Chip devices offer rapid kinetic measurements with minimal reagent use. For example, a chip can measure enzyme activity in real time by detecting product formation, similar to how a finely tuned stopwatch records the exact moment an event occurs. Immunoassays integrated on Lab-on-a-Chip platforms enable the rapid and sensitive detection of antibodies and antigens. For instance, a chip can use immobilized antibodies to capture specific proteins from a sample, much like a key fitting perfectly into its designated lock to trigger a measurable signal. Chemical sensing on Lab-on-a-Chip devices can detect a wide range of analytes through integrated sensors and microreactors. For example, a chip may analyze volatile organic compounds in air samples with high sensitivity, much like a finely calibrated nose can detect even the faintest scent. Lab-on-a-Chip platforms are used for pathogen detection by integrating sample preparation, amplification, and identification into one seamless process. For instance, a chip can quickly detect bacterial DNA from a patient's sample, much like a rapid security scanner identifies threats at an airport. In food safety applications, Lab-on-a-Chip devices can screen for contaminants such as pesticides and toxins with high precision. For example, a chip can analyze a food sample for trace levels of harmful substances, much like a lab technician uses a microscope to detect impurities in a sample. Water quality monitoring is enhanced by Lab-on-a-Chip systems that can detect trace contaminants and pathogens in real time. For instance, a chip can be deployed in the field to continuously monitor water for heavy metals, much like a digital sensor that constantly checks the purity of a water supply. Air quality analysis benefits from Lab-on-a-Chip devices that combine sampling and detection to monitor pollutants. For example, a chip can detect particulate matter or volatile chemicals in urban air, similar to an air purifier that continuously monitors and adjusts to maintain clean air. Lab-on-a-Chip platforms are valuable in biodefense by enabling rapid detection of biological warfare agents and toxins. For instance, a chip can identify anthrax spores in a suspicious sample with high sensitivity, much like a high-security alarm system quickly detects intruders. Forensic analysis is enhanced by Lab-on-a-Chip devices that can rapidly analyze trace evidence at a crime scene. For example, a chip may process minute quantities of DNA or chemical residues. similar to a forensic light source that reveals hidden evidence under specific wavelengths. Detection of chemical warfare agents is made possible by lab-on-a-chip devices that integrate sensitive sensors and rapid sample processing. For instance, a chip can detect nerve agents in the field with near instantaneous results, much like a trained sniffer dog identifies specific scents with remarkable accuracy. Lab-on-a-chip platforms are applied in nuclear detection by monitoring trace radioactive particles or chemical signatures. For example, a chip can analyze air samples near nuclear facilities to detect anomalies, similar to a Geiger counter that precisely measures radiation levels. Space exploration benefits from lab-on-a-chip devices that perform complex analyses in a compact, lightweight format. For instance, a chip on a spacecraft can analyze extraterrestrial soil samples for signs of life, much like a portable lab that fits in the palm of an astronaut's hand. Remote sensing applications use lab-on-a-chip devices to monitor environmental conditions in hard-to-reach areas. For example, a chip deployed in a rainforest can continuously monitor humidity and pollutant levels, much like a weather station collects data in a remote location to predict climate patterns. Lab-on-a-chip devices are valuable educational tools that demonstrate principles of fluid dynamics, chemistry, and engineering in a hands-on format. For instance, students can use a chip to observe laminar flow and mixing in real time, much like a science kit that brings abstract theories to life with practical experiments. Integration of microreactors in laboratory settings through lab-on-a-chip technology enables the miniaturization of complex chemical processes for research. For example, a researcher can conduct high-throughput synthesis experiments on a chip rather than in large flasks, similar to using a microbrewery to produce craft beer in small batches. 3D printing is emerging as a method to fabricate lab-on-a-chip devices with complex three-dimensional architectures. For instance, a chip with intersecting microchannels can be rapidly produced using 3D printing technology, much like constructing a complex model using interlocking building blocks. Laser micromachining offers high precision in fabricating microfluidic channels on lab-on-a-chip devices, for example. A focused laser beam can ablate material from a substrate to form intricate channel patterns, much like a skilled sculptor uses a chisel to carve detailed features into stone. Combining soft and hard lithography techniques enables the creation of hybrid lab-on-a-chip devices that capitalize on the strengths of both methods. For instance, a chip may use hard lithography for robust channels and soft lithography for flexible sensor integration, similar to constructing a building with both concrete and glass to achieve both strength and aesthetic appeal. Novel chip architectures are being developed to further expand the capabilities of lab-on-a-chip devices. For example, multi-layered chips that integrate vertical fluid routing can perform more complex analyses, much like a skyscraper efficiently uses vertical space to accommodate various functions. Microfluidic logic circuits are emerging as a way to process information directly on a lab-on-a-chip device without external computers. For instance, fluidic logic gates can control reagent flow based on input signals, much like electronic circuits in a computer process. Digital information to produce a desired output. Lab-on-a-chip technology is making its way into wearable devices for continuous health monitoring. For example, a wearable chip can analyze sweat for biomarkers related to hydration and stress, much like a fitness tracker continuously monitors your heart rate and activity levels to provide personalized feedback. The future outlook for lab-on-a-chip devices is bright as they continue to integrate advanced nanomaterials, quantum sensors, and AI-driven analytics to push the boundaries of chemical processing and diagnostics. For instance, next-generation chips might simultaneously perform multi-omics analyses with unparalleled sensitivity, much like modern smartphones combine high-resolution imaging, fast computing, and diverse connectivity into one revolutionary compact device.